Hey Chem Squad, today we're going to look at the quantum chem model for the atom. This particular atom actually has some very complex structure. Okay, so we'll look at exactly how the electrons are positioned first, and then we'll look at how everything else fits in. Okay, so unlike the other models, electrons are found in regions of space. Called orbitals. Now, they're different from the shells and the random movement of electrons. Most of these orbitals, okay, most of these orbitals are found around the nucleus. And because electrons are found in these orbitals, that also means that electrons also move around the nucleus just like the other models. But here's where they differ greatly from the other models. There are 4 orbital types. Each of these have a different kind of shape. Each of them are made up of one or more component or parts. So we'll look at the first 2, and we'll also draw out what these orbitals will look like for the first 2. The first type of orbital is called an s orbital. Okay. The S for s orbital stands for spherical. Okay, so they're spherical shape. But because the quantum mechanic model is a 3D model, we have to draw these orbitals in 3D as well. So some of you guys who are artists, you probably won't have that much of a problem. But even if you can't draw, just do your best. So if you can draw a circle like this, and if you can draw a curved little line like that, and a dotted line behind, then you've drawn yourself a pretty decent sphere. Okay. This is what an s orbital would look like. And since the orbitals always are surrounding the nucleus, at the center of this orbital, we'll put in a nucleus. Okay. This nucleus, of course, would contain our protons and neutrons. Now, in terms of the electrons can be found anywhere inside this region of space, right? So an orbital is a region of space where you're likely to find an electron. So you can find one here, or perhaps you can find one here. Okay? These electrons can move around anywhere inside this sphere. Okay. So we say that it can hold a maximum of 2 electrons inside this one orbital. Another thing to point out right now is that this sphere, this orbital, is made up of one component. So this orbital is made of one component. And sometimes these components are called suborbitals or sublevels. But the idea is there's only one component for this sphere. And you'll see what these components are like when we look at our second orbital type. So the second orbital type is called a p orbital. Okay. Now I'm not going to go into the shape just yet. I want to see if you can figure out what the arrangement is first. So for this one, we're going to draw a Cartesian plane. Okay. So you have the x-axis, the y-axis, and the z-axis. Okay. At the center, you have your nucleus. Okay. So for this guy here, I'll go with the x first. We're going to draw an infinity sign, or a figure 8. Okay, that crosses through the intersection of all three axes. This is one component to the p orbital, the first component. And inside this component, you have one electron, and somewhere inside this region, you have a second electron. Okay. So if I change colors to, let's say, orange here, on the y-axis, you have another figure 8, or infinity sign. And within this lobe and this lobe, you'll find electrons as well. Okay, so that there's two more electrons that you would find in the second component. Now finally, if we look at the z-axis, okay, this one here and this one here is where you would find the last two remaining electrons. Okay. And I've purposely drawn the one that's coming out towards us a little bit bigger than the one that's going away from us, just for that 3D illusion. Okay, but they're roughly the same size. Now, this entire thing that we have here, okay, this entire structure, this is a single p orbital. Okay, it's made from 3 components. Again, those components could be called suborbitals or sublevels, okay, but there are 3 components. You have the px, py, or pz. Okay. So these are suborbitals or sublevels. A suborbital or a sublevel is just a smaller portion of an orbital, right? So if this p orbital is made up of 3 separate components, those components are basically suborbitals. The total number of electrons that can be held by a p orbital is 6. So it can hold a max of 6 electrons. Okay. The P stands for perpendicular. Arrangement or shape. Okay, so S was for spherical, P is for perpendicular. The s orbital only has 1 component, while the p orbital has 3. Okay. These are the only 2 orbitals that you guys can draw out on your own. Okay. The next 2 orbitals are a bit more complicated. So if we move down here to the third and the fourth, okay, and we look at the d orbitals and the f orbitals. This is what we're going to see. Now, again, I'm not going to draw them out. You do actually have diagrams in your notes package that will show you what d orbitals and f orbitals are like, and I'll point out the page numbers as we go along. So this guy here, we'll start with the d's. These guys can hold a maximum of 10 electrons. Okay, while the f orbitals can hold a maximum of 14 electrons. Every subcomponent, okay, like every sublevel, subcomponent, or suborbital, right, they can only hold 2. So when we look back at our S and P's, the S itself was made up of 1 component, so it can hold 2 electrons. The P was made up of 3 components, each of them holding 2 electrons. So if we look at the maximum number that an orbital can hold and we divide by 2, that will always give us the number of components. So for d orbitals, 10 divided by 2 is 5. So these guys have 5 components. While 14 divided by 2 gives you 7 components. The shape is complex because it's made up of 5 components, and they all have a very different shape to it. But when they all overlap, it resembles more or less a diamond shape. For the f orbitals, the shape is also complex. And when all the orbitals overlap, okay, I don't know what the F actually stands for, but it does kind of look flower-like. So I don't know, maybe a floral shape. Okay, but don't quote me on this because I have no idea what that F is for. Okay, but the shape itself is pretty complex. Okay, so I would see pages 5 to 9 in the notes package. For diagrams. And when you see them, you'll know why I don't draw these out. Okay, I don't expect you to be able to draw d and f orbitals out. However, I do expect you to be able to draw s and p orbitals. So let's look at an example. If I want you to draw an atom using the quantum model, let's pick lithium because we did use lithium before in the Bohr model. Okay. Lithium contains 3 electrons. Okay, and that's the total amount. Okay. So if we start off with a nucleus, okay, just like any atom, every single atom must begin with an s orbital. Okay. So here's my s orbital. So I'll just label this as the first s orbital. Okay. If I were to place just 1 electron, like this, I would actually have hydrogen. Okay, because hydrogen only has 1 electron. And that electron is found in the first s orbital. if I add a second electron in here, I've now drawn out helium, which is the next atom. Okay, now that's 2 electrons. Lithium has 3. But I cannot put a third electron in the s orbital. Okay, it doesn't fit. The s orbital is already full because it can only hold 2. So instead, I need a second s orbital. Okay, so this is my second s orbital. With the second s orbital, it can hold a maximum of 2, but all I need to do is put 1 in. And I can put that 1 electron anywhere inside the s orbital. Okay, so this is my third and final electron. And once I have that in here, this is my lithium atom, according to the quantum mechanic model, okay, or quantum chem model. Now, I'm going to show you, when we get back into the classroom, how to draw more complicated atoms that involves p orbitals. Okay, so the larger we go, the more orbitals there will be. And unfortunately, all these orbitals will overlap each other. So you have to draw it on top of each other. Okay, and that's why I don't get you to draw any atoms that are too large, because it gets very messy and very complicated. But like I said, we will look at more examples when we get back into the classroom. Until then, have a good one.